Welcome back everyone into another video in the series of the Laplace Transform. In today's video, we're going to cover how to solve some simple homogeneous ODEs by using the Laplace Transform. So we have the following ODE on screen. We have y double prime plus 6y prime plus 5y equals to 0. We're given so many initial conditions that y of 0 equals 4 and 1 prime of 0 equals 0. And we're given the definitions on the side of what the Laplace transform is for each single derivative. You can see that we take the Laplace transform of a function. In this case, y, it would just be the corresponding Laplace transform. The Laplace transform for a derivative, in this case, f prime, is equals to s times the Laplace of f minus f naught, which in this case will be the initial condition. And the Laplace transform of a second order will be s squared plus the Laplace of f minus s times the first initial condition minus the second initial condition. And this process follows the same thing if we had like a higher order, etc. But at least for now, this is all we need. But you can see the pattern that basically it's made. So the first step that we need to do is the following. We need to first take the Laplace of each term. That's what I like to do. So let's start with the Laplace of y double prime, going from left to right. And you can see that I'm just going to be replacing the Laplace of f, or in this case, we have y. So we're replacing lowercase y for capital Y. So make sure that whenever you're writing this, you make a difference between the lowercase y and the capital Y, as the lowercase y represent a function of t, and the capital Y represents a function of s, or the Laplace of yt. So following the formula as seen on screen, the Laplace of y double prime, it's s squared times capital Y minus s y naught minus y prime of 0. And if we substitute those values there, you can see for y of 0, we have 4. So we're substituting that value there. It will be s times 4. And then for y prime of 0, we have that it is equal to 0. So we just substitute 0 there. And then we're left with s squared capital Y minus 4s. Continuing, we have the Laplace of 6y prime. And you can see here, since 6 is a coefficient, we can factor it out. And then it will be multiplied times everything after. So the Laplace of y prime, it's s times capital Y minus y of 0, where we have seen before that y of 0 is just 4. So we can substitute that value. And after we distribute the 6, we're going to get 6s capital Y minus 24. Continuing like that, we see that the Laplace of 5y is just 5 capital Y, as I told you before. And after this, we just write it back into the equation. So we're going to have s squared capital Y minus 4s plus 6s capital Y minus 24 plus 5y equals to 0, because the Laplace of 0, it's 0. So after this, I'm gonna factor out a y and then trying to solve for that capital Y. So if I factor out the y, you can see that I'm gonna end up with capital Y times s squared plus 6s plus 5 minus 4s minus 24. Once again, you can see that we changed from a differential equation problem into making it into an algebra problem. This is where the Laplace comes in handy, because I don't have to do any calculus, at least for now. And all that happens is that I make my problem from a differential equation problem into a simple algebra problem. So if I continue, I send the 4s to 24 to the other side. And then I divide by the s squared plus 6x plus 5. And I have that y. And that one in the bottom, we can factor out. So you can see that capital Y, or the Laplace of y, in this case y of s, that's actually what it is, it's equals to 4s plus 24 over s plus 1 times s plus 5. And you can see I put a note here that this is not the final answer. This is like our halfway point. Here, right, this answer right here, it's our solution in the s domain, but we want our solution in the t domain. So what I need to do now is basically take the Laplace inverse so I can find my y of t. So You can see I'm gonna take the Laplace inverse of y and solve for y of t, or lowercase y. So if I take the Laplace inverse of capital Y, we get y of t. So I'm also substitute there. So we have 4s plus 24 over s plus 1 and s plus 5. I need to take the Laplace inverse of that. There's many multiple ways in which we can do this. We can use the formulas, we can use convolution, we can use partial fraction decomposition, any method, whatever the case you have here, it's valid. Sometimes we don't even need to do any of those. Sometimes it's just a matter of rearranging things and, until we have something that we can actually take the Laplace inverse of. At least for this one, what I'll do is I will do PFD. So you can see I can break it up into its two corresponding fractions, a over s plus 1 plus b over s plus 5. And I need to find out what a and b are. So I will do the cross multiplication so that they have the same denominator. And then once you can see they have the same denominator, I can equal the tops or the numerators. So 4s plus 24 is going to be equals to a times s plus 5 plus b times s plus 1. I will just simply distribute. I get one equation, two unknowns. So I will do my equating the coefficients. So on the terms that have an s, I have a plus b equals to 4. And the terms that are constants, I have 5a plus b equals to 24. So starting from here, I can rearrange. I can find b. I can substitute it back, and I can get, therefore, that a is 5 and b is -1. So substituting a and b on my initial on what I initially wrote, for the PFDs, I will get 5 over s plus 1 minus 1 over s plus 5. Take the Laplace inverse, and you can see we have that definition where e of at is the Laplace of 1 over s minus a. So doing that, we're going to get it's equal to 5e to the negative 5t minus e to the negative 5t. So this is my final answer. I have that the solution to this differential equation is y of t is equals to 5e to the negative t minus e to the negative 5t. And this problem, you want to check it, you can solve it any other method that we have used before, like the undetermined coefficients. Use that one and you will find out that this is actually that answer as well. There are instances with Laplace, as maybe for this example, can seem that it's longer, but you'll see as we get on harder questions that Laplace is actually a really useful tool, especially on instances, as we'll see in later videos, that we cannot really write a number for cases where we have impulses or step functions or things like that. So that's it for this one. Let's see another example. In this one, we have y double prime plus 2y prime plus 10y equals to 0. And the initial conditions are 1 and 0. So you can see that, once again, take the Laplace of each. The Laplace of y double prime is s squared y minus s times y naught minus y prime of 0, which if we substitute the y prime is 1 prime of 0 is 0, and then the y of 0 is 1. So this will result in s squared times capital Y minus s. If we take the Laplace of 2y prime, factor out the 2, take the Laplace of y prime, which is s times capital Y minus y of 0, which we know it's already 1. Multiply back the 2, and we're going to get 2s capital Y minus 2. We have here, once again, the Laplace of 10y is just 10 capital Y. And the Laplace of 0 is 0, so write it back to get into the equation form. We have s squared capital Y minus s plus 2sy minus 2 plus 10y equals to 0. Factor out a y. We have capital Y s squared plus 2s plus 10 minus s minus 2 equals to 0. Send those terms to the other side. Divide by y. And then this one, we can factor it out. Well, I guess technically, well, in this one, we couldn't actually factor it out, right? It's s squared plus 2s plus 10, you cannot. But we can basically complete the square. So we get 2 divided by, we divide it and then square that number. So we're going to get s squared plus 2s plus 1 plus 9, right? That's a way in which we can split 10. And we can write like this, of course. And then the s squared plus 2s plus 1, that's a square number. That is s plus 1 square. And then we know that the 9, it's a 3 square. And look what we're going to be doing for this problem. So I see, you can see the pattern, what we're doing. All we have done so far is just rearrange the bottom. In this case, once again, we started with s squared plus 2s plus 10, which does not have a factor. It cannot be factored out. So then you cannot do PFD if that's the case, if we cannot be factored out. So what we do is we rewrite it. We split the 10 into 1 and 9. 1, what happened to be the perfect square for that one to be s plus 1 square. And then 9, we know it's a 2 square. You can see that this is already taking shape. Now, if I continue, you can see that I can split the top as well and to have s plus 1 plus 1, right? And then now with this, I can just group it in parentheses. I can want to factor out, find, of course, my y of t. So I will take the Laplace inverse of that. And you can see on this one that we have s plus 1 both on top and bottom. And if you recognize this from the previous videos, you will note that this is actually an S shift, right? So if this is an S shift, it means that there should be an exponential. So we're going to substitute, the S plus 1 was substituted for S. So we change that. And then, so instead of s plus 1, we have now s plus 1 on top. In the bottom, we have s squared plus 3 squared. And we can split that into 2 separate fractions, s over s squared plus 3 squared plus 1 over s squared plus 3 squared. And out of that, s shift, is translated into an exponential in the t domain. And you can see that solving this one, we are going to get, if you remember the Laplace transform for sine and cosine, this is basically what they are. So we get essentially an exponential times cosine of 3t plus 1 over 3 sine of 3t. And that is, in fact, our final answer for this problem. So you can see that for this one, we did not do PFD or any formulas or convolution or anything. All that was required was for us to basically rewrite the terms and manipulate them so that they actually become something that we actually know, right? In this case, it was sine and cosine, but it's a matter of recognizing what we have. It might take a while, but the more problems that you solve like this, you can see that some things start popping up in your mind, and you can start recognizing the patterns, and you will start knowing what terms I need to manipulate algebraically so that I can solve problems and make it easier. So that comes with practice. And the last problem that we have, it's y double prime plus 16y, and this is equals to e to negative 2t. So in this one, you can see this is not a homogeneous problem. This is actually a non-homogeneous problem. We have both initial conditions to be equal to 0, but the process is exactly the same. So instead of using the method of what's the variation of parameters or the undetermined coefficients, we can simply use Laplace. So let's do like we've always done. We have the Laplace of s squared y minus s times initial condition of y minus y prime of 0. And basically that would, if both initial conditions are 0, we have simply s squared plus y times y, capital Y. We take the Laplace of 16, which is just 16y. And we also take the Laplace of e to the negative 2t, which will be, of course, 1 over s plus 2. So we write it back into the equation, just like this. You can see we factor out y. We have s squared plus 16 equals to 1 over s plus 2. We divide by s squared plus 16, and we have therefore that capital Y is equals to 1 over s squared plus 16 times s plus 2. So we want to find y of t, of course. So what we'll do is we take the Laplace inverse of all of that. we have 1 over s squared plus 16 times s plus 2. We can use partial fraction decomposition. You can see that for the first term, because the power on the bottom is a square, the power on the denominator has to be 1 less. Therefore, instead of just having a over s squared plus 16, we should have as plus b, going all the way down to the constants, over s squared plus 16. And the second one, we only have the c because the bottom it's a power of 1, so the numerator should be a constant. So doing this, I will want to solve for as. So for a, b, and c, I will of course do cross multiplication. The numerators will equal to each other. So that's how I get my equation. I will basically just distribute. I get my equation. I will need to then equate the coefficients. So for s squared, I have a and c equals to 0, where we can get that c is equal to negative a. For s, I have 2a plus b, once again equals to 0. And then for the constants, I'll have 2b plus 16c equals to 1. So solving from here, we can do some substitutions. We can find that a is equals to negative 1 over 20. We find c is equals to positive 1 over 20. And then b is equals to 1 over 10. So I'll plug those numbers back into the terms that I have before. And I can, of course, factor out the a, b, and c. I can just substitute the values later. And you can see that I will get here the first one, s over s squared plus 16, will look like a cosine of 4t. The second one is like a sine divided by the omega. And the last one is just an exponential. So after I multiply everything, this is our final answer. Negative 1 over 20 times cosine of 4t plus sine over 4t over 40. You can see we have first 1 over 10 times sine over 4. So that ends up being over 40. And the last one, 1 over 20 is the negative 2t. So those are the problems in which we have to use Laplace to solve ODEs. I hope that this video has been really helpful. And until next time, good luck.